Hello everyone. This is the next video in sequence for the logic gates and logic circuits. Before this, we discussed key terms, logic gates, logic circuits, truth tables, and Boolean algebra, and we defined few steps required to cover the topic. The first one was knowing gates and drawing circuits that we completed, finding mathematical equations and Boolean expressions out of the logic circuits and the conversion between the two. Third was making circuits out of equations and expressions. This we have covered. Now, today we will cover truth table, building blocks, past paper questions, and understanding real world scenarios. Their related logic, devising equation and expressions for them, and making circuits out of it. So we will be doing this part 4 with part 7 past paper questions together. So let us start with the truth tables. Truth tables, first of all, let us discuss what are the truth tables. Truth tables are the tables that actually give us an idea before making a circuit in physical form that what would be the output for those circuits. Means it gives all the possible outputs which we can expect from a circuit that we have designed. So truth table is a method of checking the output from the logic circuit. They use all the possible binary input combinations depending on the number of inputs. What does that mean? It means that every single equation that we actually see, you can see over here, there is an equation where we have got just one variable A whose output is X, and we have got over here in this equation two variables A and B, and in this equation, if you could see, we have got A, B, and C. I told you earlier in previous episode that no matter how many times a single variable reappears, it will still be counted as 1. So if A is appearing twice over here or C is appearing twice over here, they will still be counted as 1. So then in this third equation, we have got 3 variables. So the size of the truth table is basically dependent over the number of inputs in the circuit the truth table is representing. So over here we have got just one input, which is A naught. So we will be actually trying to make a truth table which will be representing A naught. Now what you have to understand is first the possibilities, working out the possibilities. As I said that truth table use all the possible binary input combinations. So the possibilities are all the possible binary input combinations. So how do we define what is the number of those possible combinations? And we have to cover those possible combinations in a way that nothing is left. All the possible inputs which can be there should be covered. So first you have to understand this formula, which is 2 to power n. 2 to power n means 2 is the base. This logic circuit is all dependent on Boolean algebra, zeros and ones in binary logic. So it means that if there may be anything which can be given and taken out is just zeros and ones. So this is the base 2 system. And this n is the number of inputs. What are the number of inputs? Number of inputs of the variables. So if we see an equation has got one variable, it means that this is 2 to power n. If you see equation, it has got two variables, then it means that 2 to power 2. And if we see an equation has 3 variables, then it means it is 2 to power 3. So in this equation, it is x is equal to a naught. So it means that there is just one variable a. So this is 2 to power 1, which becomes 2. And it has got 2, x is equal to a exclusive for b. So 2 to power 2 means 4. And this equation ab naught exclusive for a plus c whole naught multiplied by c, it has got 3 variables, which means that there are total 2 to power 3, 8 possibilities. Now, when we count in computer, we always count from 0. So if it is 2 possibilities, it means that it is 0 and 1. And if it is 4 possibilities, it means it is 0, 1, 2, and 3. And if there are 8 possibilities, it means that it is 0, 1, 2, 3, 4, 5, 6, and 7. 0 to 7, we have got 8. Now let's see over here. Every truth table has got 3 parts. Number 1, input part. Number 2, working part. And number 3 is the output part. So input part would be comprised of all the variables in it. So this equation has got one variable. So this is the input part, which only shows one variable A. So this is 0 or 1. This equation has got 2 variables A and B. So it shows 2 variables A and B. Now, as you can see over here, this is quite obvious that there are 2 variables as input. So there are 4 possibilities. How do we devise these possibilities? How do we make them? How do we actually find the combination for one single input to the circuit in the form of having zeros and ones under the variables? The thing is, if you know the binary number system, you would have an idea that every single digit in the count would have its own combination of zeros and one. This is the combination according to that series. If you could see that 2 variables, if there are 2 variables, it means that these 2 variables can be taken as 2 bits. And in 2 bits, this is 0. In 2 bits, this is 1. In 2 bits, this is 2. In 2 bits, this is 3. Similarly, for this particular expression, logic statement, we have got 3 variables. So 8 possible combinations, 8 possibilities are there. So those would be 0, 1, 2, 3, 4, 5, 6, and 7. 8 possibilities. But you need to understand that since there are 3 variables means 3 bits. And in those 3 bits, you have to find the combination in the binary form for 0, 1, 2, 3, 4, 5, 6, 7, and 8. So if you could see over here, this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and 7. So it is quite clear over there that these are basically the serial numbers 0, 1, 2, 3, 4, 5, 6, 7. And if we divide them, if we devise them in the form of binary, and that binary would have as many bits as the number of input variables, we can easily find these combinations. Sometimes people go for 1 0 1 1 1 0 1 1 and then 2 zeros 2 ones and 4 zeros and 4 ones, but that is not a learned way. You should know how do we devise these possible inputs. So the possibilities, the number of possibilities is devised from the number of variables as input, and total possibilities combinations are devised as the series in binary form, and that series is actually written or list down in the number of bits as many as the number of variables in the equation. Afterwards, when we try to solve for this first equation, this is x is equal to a naught. So it means that if we have got a, so the inverse of that or means a naught would be x. So if it is 0, it becomes 1. If it is 1, it becomes 0. For that second expression, we have got a and b. So first we find out the total possibilities, the combinations for the input, and then we have got what? Output. A exclusive for, as we know that exclusive for defines that if the both inputs are the same, the result would be 0. If both inputs are different, then the result would be 1. So in other words, in layman terms, we cannot choose everything. We can choose either of the things, but not everything. So if you try to choose everything, means all ones, that answer would be 0. So you could see over here that if A and B both are 0, it is 0. If A and B are 0, 1, then answer is 1. If A and B are 1 and 0, answer is 1. And if they both are 1, as I said, it would not be allowed, so it is 0. In here, it is a complicated one. So what we have to do is to take bracket by bracket and we will solve. Mind one thing, we will never have more than 2 inputs in a single gate. We may have many inputs in the circuit, but we may not have more than 2 inputs in a single gate. So these brackets actually pave a way to keep this thing simple. Means in the absence of brackets, we might have several inputs together in the single gate, and that is not actually the requirement of CAIE for O level and AS level. So we have to strive, we have to put in effort to make it always possible that there should be 2 inputs per gate. With those words, we get to the next multi-input logic gates. As you can see over here, as I said that multi-input logic gates, for multi-input logic gates, we cannot have more than 2 inputs. So what we have to do is we have to understand that if a gate, maybe AND or it has got more than 2 inputs, we have to convert it this way. So if A and B and C means, if it is like this, A and B and C, so we have to make it A and B, put a bracket, and then C, put a bracket. That is how it will be done. Similarly, if we have got A or B or C or D, in that case, we would have a solution for having just 2 inputs per gate this way. A or B over here, plus C over here, plus D over here. And this whole thing goes to X. So that is how you would have to understand that you have to put brackets left to right to maintain just 2 inputs per gate. In any of the cases, over here or over here, the result would always be the same. It really does not matter if you add 1, 2, 3, 4, 5 together, or first you add 1 plus 2 and then the result will be added to the 3, and then result will be added to 4, and then result will be added to 5. This will always remain the same, but this was just a lame analogy. It doesn't apply to binary form. So in binary form, the result of these 2 circuits, no matter what, would remain the same. So always try to avoid multi-input logic gates and try to devise an equation or a circuit which is actually having just 2 inputs per gate. Now let's get down to this part, back to truth tables. You can see I have drew all the possible outputs for every gate over here. You can observe it easily. So we have got just these 2 inputs per gate. So this is our AND gate. This is A, B, and the result is there. This is OR gate. This is NAND gate. This is NOR gate. This is exclusive OR gate. And this is A naught, and this is B naught. So you can observe it. If it is AB, as I said that AB is being represented using multiplication, and you cannot choose one thing. If you would have to choose, you have to choose both. So if it is both zeros, then it is 0. If it is 1 0 in any form, it would always be 0. So that is why we represent it with the mathematical operator multiplication. If they are all ones, only then you have 1. In OR gate, until unless there is 1 1 in the equation or input, the result would always be 1. And we can take it like If you want to choose any of them or all of them, you are allowed to do that. So until unless you don't want to choose both zeros, the result would be 0. Otherwise, result, if there is 1 1 or more than 1 ones, would always be 1. This is a mistake. Hold on. Now, we have got NAND gate. In NAND gate, you can see that this is always an inverter of AND gate. So if it is 0 in A and B, it will be 1. So wherever we have got 0, that will become 1. And wherever we have 1, that will become 0. So that means that whatever the output of AND gate will be inverted, will be not, will be opposite to whatever the AND gate result is. Similarly, that is true for A plus B whole not. That is NOR gate, not OR. So whatever the result of OR, it will be inverted in not OR gate. Now you can see if it is 0, it becomes 1. If it is 1, it becomes 0. If it is 1, it becomes 0. If it is 1, it becomes 0. In exclusive OR, I have already discussed that whenever there are inputs, they are same, the result would be 0. So if we have got both zeros, then the result is 0. If we have got both ones, then the result is 0. If in any other case, it would be 1. And then we have got A naught and B naught. A naught can be represented using a bar or a trine. It is up to you. So only AND gate would have, only NOT gate would have one input, and rest of the gates would have always 2 inputs at least. NOT gate would always have in every case just 1 input. So A naught is whatever the result of whatever the input in A, that will be inverted. So A is 0 0 1 1, so it would become 1 1 0 0, and in B it is 0 1 0 1, so it would be inverted to 1 0 and 1 0. So that is how we find out the inputs, total number of inputs for the logic gates, and then we work it out to find the output of it. Now, let's get back to these steps required to cover the topic. So truth tables, we discussed truth tables, and then we discussed multi-input logic gates, and afterwards, now we are going to discuss building blocks. Building blocks are actually the use of NAND and NOR gates to define any of the circuit. As we discussed in the last lecture, that NOR and NAND gates are actually able to create any other single same output holding circuit. So let us discuss those. So as I said, that building blocks are actually either NOR or NAND gates. So common building blocks are either NAND or NOR gates. It is possible to build up any logic gate or logic circuit by simply linking together a number of NAND or NOR gates, which are called building blocks. As you can see over here, CAIE does not require you to have a lot of knowledge of it. This is very simple. So if it is just AND gate, we can create AND gates output by having 2 NAND gates linked together. As you can see, these 2 inputs goes to this first NAND gate and the output becomes couple of those and they enter another NAND gate, and we can always use truth tables to find out that the output of AND gate and building blocks NAND logic would be the same. And then we have got three NOR gates connected together to form the same output as we are having with the AND gate. So if we create a circuit or a gates alternative using NAND gates only, then it is said to be NAND logic. Otherwise, if we are using NOR gate, then it is said to be NOR logic. It is not asked until now to use NOR gates or NOR logic in exam, but this is expected, so you would have to learn it. For NOT gate, we have got same one single NAND gate would have same output as NOT gate, and one single NOR gate would have same output as NOT gate. And then OR. As you can see, as you can observe over here, one AND gate can be created using two NAND gates, but can be created using three NOR gates, whereas one OR gate can be created using three NAND gates but two NOR gates. So this might be one more thing to remember and would be easier for you to remember the conversion. So one AND gate can be created using three NOR gates and two NAND gates, whereas one OR gate can be created using three NAND gates and two OR gates. Whereas for NOT, we can always use just a single gate. So one NAND gate would have the same output as NOT gate if there is just one input which is being doubled and going into the NAND gate. Similarly, one NOR gate would have, if a single input is being doubled and going into NOR gate, would have same output as NOT gate. So this we have to remember. Let's get back to the steps that we required. Now, truth tables are covered, building blocks are covered, multi-input logic gates are covered. Let's now cover the scenarios, real world scenarios in past papers together. What does it mean when I say real world scenarios? Real world scenarios are, for us at O-level and AS level, are those problems or statements or scenario given in exam questions which we have to read and then convert it to the logic circuit. For actual world, whatever the need for the machines to be created for, when those needs are analyzed, first their circuits are designed and then designed on paper, and then they are physically built up. So the whole designing is called the engineering, electronics engineering. So real world scenarios are for us just those short problems that are presented in questions. So let us see few of those. I have tried covering all different sort of past paper questions, and I hope that this will cover every sort of question. So oldest to latest order, let's cover all these past paper questions. Complete the truth table for this circuit of logic gates. So what is C? So over here, C is actually A naught. So it means if A is 0, C would be 1. If A is 0 over here, if A is 0, then C is 1. If A is 1, then C is 0. If A is 1, then C is 0. Now what is D? D is A plus B, because this is OR gate. So A plus B means whenever there is a single 1, the output would be 1. So both zeros means 0, 1, 1, and 1. So what is at the end? What is out? Out is equal to A naught and A plus B. This is the result. It means that these two are being ended. These two are being ended. So So C and D are being ended. So if there is a single 0, answer would be 0. Both ones, then answer would be 1. And then we have got 1 0 and another 0. So both will be 0. So this is your truth table for the first question. Now for the next part, one thing that you have to understand is that it is not in AS or O, but there are questions related to it. There's a topic called adders. Adder means those circuits which take one input, a couple of inputs and add the values together. Adders. Adders are doing summation operations in arithmetic and logic units, arithmetic part. So adders will always have two outputs. The name of the output would be a carry and sum, C and S with that respect. So whenever you see a circuit that is having two outputs, you would have to check the name, the variables assigned to outputs. If those are C and S, then it means that it's an adder, because there would be a related question that what is the purpose of that circuit. If there is one output, no worries. But if there are two, you would always have to understand. As you can see in this particular question, there are two outputs, but their names are E and F, so no worry. So what is E? E is actually A plus B, and this output is inverted. So this is E. So this is NOR gate basically. Sorry. Output is E. And then we have got F. What is F? A plus B whole not, again plus B whole not. So the result, you can say that this is E. So this would be E plus B whole not. Now, so let's first do this. A plus B whole not means it is NOR gate. A plus B whole not. So this is 1, this is 0, this is 0, this is 0. In OR gate, this would be 0, 1, 1, 1 because it is NOR. So this is 1, 0, 0, 0. And then E plus B whole not. So E plus B whole not. E plus B would be 1. So this would be 0. This would be 0. this would be 1 and this would be 0. How? Because E plus B in this case will be E plus B in this case will be 1, 1, 0, 1, and because F is the inverse of it, so 1 becomes 0, 1 becomes 0, 0 becomes 1, and 1 becomes 0. So this is your output. Now, next part. Over here, again, there is a circuit, but this time circuit with output, two outputs, but this time the name of the output variables is S and C. S is as sum and C as carry. So whenever the output is sum and carry, it means this is simply an adder. A circuit that adds or sums input. It is found in ALU. So this is it for O and AS level. At A2 level, we have to study it further. So now what is W? W is A plus B. What is X? A, B whole naught. And what is C? It is simple AB. And then what is S? S is actually X and W. So let's solve it. A plus B, 0, 1, 1, 1. A plus B whole naught, 1, 0, 0, 0. So not A plus B whole naught, rather it is AB whole naught. So AB would be 0. It becomes 1. Over here it becomes 1, it becomes 1, and it is 0. Okay. Now C is simply AB. So it is 0, 0, 0, 1, and X is actually X and W. So X and W are these two. X and W. So X and W would be 0, 1, 1, and 0. So since it is an adder, you can see that this is carry and this is sum. What does it mean, sum and carry? If you could see, if you find it like these are 2 bits binary, this is 1 and this is 2, as in this is 2 to power 0 and this is 2 to power 1. In that case, this should be 0, 1, 2, and X and W. I have made a mistake. So this should be, no, this is 2. This is 1 and this is 2. You can see easily. So 0 plus 0 is equal to 0. There we go. 0 plus 1 is equal to 1. There we go. 1 plus 0 is equal to 1. There we go. 1 plus 1 is equal to 2. So this is binary 2. There we go. So mind it, as you can see in part B, state a possible use for this circuit in a processor, and you can see that that adds or sums inputs. So it is found in ALU. The purpose of this, the purpose of this circuit in microprocessor is to add two inputs. It is called adder, and it is found inside ALU of the microprocessor. I hope that you got the idea over here. Let's move on to the next question. So it says that x is equal to 1 if A is 1 and B is 1. It means that it is AB, or B is 1 and C is not 1. B is 1 and C is not 1. B, C, not. So this is actually x is equal to AB plus BC not. So AB means we have to put AND gate over here, and then BC not. This is again AND gate, B, and we have to convert C to its not form, and then there is OR gate, which is going into OR gate. So as you can understand over here, so this is AB, this is BC not, and this is their OR. Now, as you can see, we have already found the equation. Equation is AB and then BC naught let's find C naught, then we have what, BC naught, and then we will work it out into X. So the equation is X is equal to AB plus BC naught. Let's solve it. First of all, AB. So this will be 0, 0, 0, 0, 0, 0, 1, and 1. You can see this is AND gate, so whenever we have all ones, answer is 1. In any other case, answer is always 0. Now C naught. So C naught will be easy. Whatever's the C, we have to invert it. So 1 0 1 0 1 0 1 0, and BC naught. BC naught means we have to consider this B and C naught. Now B and C naught would be over here 0 0 1 0 0 0 1 and 0. So this is very simple. B is 0, C naught is 1, so this is 0. B is 0, C naught is 0, this is 0. B 1, C naught 1, then it is 1. B 1, C naught 0, it is 0. And similarly, at the end we have B is 1 and C naught is 0, so the answer is 0. Now for X, we have to actually take into consideration this AB and BC naught. These two will, when we OR, means added together, the answer would be X. So either of them, if it is 1, the answer would be 1, and if they all are zeros only, in that case the result would be 0. So this is 0 0 1 0, 0, 0, 1, and 1. So you can see this is 0, this is 0, answer is 0, this is 0, this is 0, answer is 0, this is 0, this is 1, answer is 1, this is 0, this is 0, answer is 0, this is 0, this is 0, answer is 0, this is 0, this is 0, answer is 0, this is 1, this is 1, answer is 1, this is 1, this is 0, but answer is 1. That is how we do it. Now, next question. We have to pay attention to these brackets. A is not 1 and B is 1, or B is 1 and C is 1, and then we have got upper brackets, or C is 1 and then we have got final brackets. The whole thing is assigned to X. So first we have to find A not B. So A not B. A not B, and then B, C, B and C. They will be odd, and then their result will be odd with C. This is your answer. So first we have to find A not B. This is A not B. Then we have to have B and C. This is B and C. Then they both are being odd over here. There we go. And then the result will be odd with C. There we go. So the equation goes like A not B, A not B plus B and C plus C. The whole thing is assigned to X. So we have to find first of all A naught. Then we have to find A naught B. Then we have to have B and C. And then we have to have this whole thing, A naught B plus B and C. A naught B plus B and C, let's call it M. So we have to have M. And then when M will be odd with C, the answer would be X. So A naught. A naught would be 1, 1, 1, 1, 0, 0, 0, and 0. A naught B will be 0, 0, 1, 1, 0, 0, 0, and 0. Because whenever there are two ones, only then we will be able to get one, otherwise we would always have zeros. Now B and C. B and C 0, 0, 0, 1, 0, 0, 0, 1. Now M. M is actually A and A not B plus B and C. So these two only. Now 0, 0, 1, 1, 0, 0, 0, 1. And if we add this M to C, then we get X. So 0, 1, 1, 1, 0, 1, 0, 1. That's your answer. Now, you can always pause and understand this. I cannot stop, but you can always pause the YouTube video, and YouTube can wait for it. So do not just let it go. Pause it, understand, and then go further. Now, for this question, This is a bit tricky and different question you have to understand. A combination of three lights is to be shown in a set sequence at a rock music concert. The three lights are red, green, and yellow. Red is being represented using R, green is being represented using G, and yellow is being represented using Y. The following sequence is followed. Red only for 3 seconds, red and green for 1 second, and yellow only for 3 seconds, and green only for 1 second. A counter is used which consists of 3 bits A, B, and C. The counter is incremented every second and recycles continually. A logic circuit is to be built to generate a sequence of lights. A Boolean value of 1 represents the light switched on. The lighting sequence starts with red only. As you can see with this description, in exam you would have a lot of trouble to understand and answer such question. It is always a good idea, since the questions in computer science, they are related. In one particular question, all parts are related. So what you have to do, if you don't get one part, there is always a rolling effect of that first part into second. So most of the times when you get to the second part, you get it what was required in first part. Mostly this doesn't happen, but if it happens that you don't get one part, all you have to do is to move on to second part. Second part would definitely have a hint to the solution for first part. As you can see in this part, this is quite complex to understand what they are saying and how do we come up with the truth table and the circuit. So what we have to do is we have to move on and see what is in second part. So in second part, it says that R is equal to 1 if A is not 1. So it means that what is R? R is only A naught. Then it says G is equal to 1 if B is 1 and C is 1. So what is G? B and C. And Y is 1 if A is 1 and not B and C. So it means that A into B and C whole naught means A into G naught. This is very simple. Okay. So now what is R? R is simple, A naught. So this is 1, 1, 1, 1, 0, 0, 0, and 0. What is G, B, and C? So 0, 0, 0, 1, 0, 0, 0, 1. What is Y? B and C naught multiplied with A. So what is B and C naught? So let's first solve B and C naught. B and C whole naught. So what is B and C whole naught? B and C is G. So 1, 1, 1, 0, 1, 1, 1, 0. So this B, C naught, when it will be ended, A and D ended with A, the result would be Y. So 0, 0, 0, 0, 1, 1, 1, 0. That is very simple. So that is how you will be able to solve those. So remember, when you don't get it in first part, you would definitely be having a hint in second part for the solution of first part. Now, so there is the requirement of drawing the logic circuit. So what is R? R is A naught. So that is very simple. A naught is R. G, what is G? B and C. So B and C is actually G. Now what is Y? A naught and not B and C. A naught and A naught and not B and C. This is Y. That is very simple. A naught and B and C whole naught. That is Y. I hope that you got it. If you don't get it, do watch the first part once again. Now complete the truth table for the following logic circuit. This is A plus B whole naught. This is A and B. This is A plus B whole naught plus AB and completely whole naught. And this X is equal to A plus B whole naught plus AB whole naught multiply with C naught. You can solve it this way. Now pause and solve it yourself. Now this is the question I call real world scenarios. So such solutions would be required by you. So let's solve this question. A car has an engine management system, EMS. The EMS outputs the following signal. A is 0 when temperature is within limits. A is 1 when temperature is too high, that is a fault condition. And B is 0 when the pressure is within limits, and B is 1 if the pressure is too high. So A is related to temperature, B is related to pressure, and we can see that this is some sort of sensors output which is being used as A, B, and C over here. C is the carbon emission within limits, and carbon emission if they are too high, that is a fault condition. So they say that draw a logic circuit following the fault conditions. So if all three signals A and B, C indicate a fault, so it means that driver is want to stop the engine, means all three signals A or B or C indicate a fault. The driver is want to stop the engine, output is equal to 1. So when they all are 1 or all three signals indicate a fault, so it means that all three indicate a fault. The driver is want to stop the engine. It means it is not AND gate, this is an OR gate. All three signals A is equal to 1, B is equal to 1, C is equal to 1 indicate a fault. So whenever A is 1 or B is 1 or C is 1, this is a fault condition. If you do remember from that multi-input gates, for multi-input gate this would be A or B or C, then the result is 1, which is X. But for us it would be A or B or C. The result would be 1. So if any of them, they all indicate the fault. If any of them is the drivers want to stop the engine, output X is equal to 1. So if it is an AND gate, that would not serve the purpose. It has to be OR gate, because if any of them is actually OR gate, is 1, then OR gate would serve the purpose. Move on to next question. Now, draw a logic circuit for the following fault condition. Either A and B is equal to 1, or B and C is equal to 1. Then Y is equal to 1 over here. The drivers want that the engine needs a service, so Y is equal to 1. So this should be Y. Now A and B, B and C, and OR gate. If any of them is having one output, the result would be Y as 1. A is equal to 1, B is equal to 1 means AB, or this is OR, and over here this is OR. B is equal to 1 and C is equal to 1. Okay, so if these two are 1, then we would have 1 over here. If these two are 1, any of them are 1 means the output would be 1. Now over here you can see either A is equal to 1 or B is equal to 1 or C is equal to 1. So this is same. A is equal to 1, B is equal to 1 or C is equal to 1. In all these three cases, the result would be 1, indicate a fault. So you have to create it this way. So you have to put bracket on this first and then this. As you can see over here, so X is A or B, or A and B and C, and Y is A, B, or B, C. So I have solved it over here, N plus M, and Z is A or B or C. So we have solved it over here. So you can see it, you can try it yourself, pause and understand and go further. Next question. A wind turbine must shut down when certain conditions are met. The three variables and the conditions which dictate their values are shown in the table. So W is wind speed, P is oil pressure, T is the motor temperature. So a logic circuit is to be designed where the output X is equal to 1 if either wind speed uh, is 100 kilo per hour or and oil pressure is normal. So if wind speed is equal to 100 kilometers per hour, so that is W is equal to 1 and oil pressure is normal means P is equal to not 1. Remember, 0 is never used, it is always not 1. Or motor temperature is equal to 50 degrees. So motor temperature is equal to 50 degree means T is equal to 1. Every line would have its own brackets. T is equal to 1 and oil pressure low means P is equal to 1 and P is equal to 1, oil pressure low. Now, or wind speed is equal to 100, W is equal to 1, and motor temperature is 50 degrees C, and motor temperature is 50 degrees C, T is equal to 1. So the expression becomes X is equal to 1 if W is equal to 1 and P is equal to not 1, or T is equal to 1 and P is equal to 1, or W is equal to 1 and T is equal to 1. Now we can see that there are two ORs, so we have to put brackets to make it further clear. So this would be W P naught plus T P plus W T, and we have to put extra brackets to make it always two inputs per gate. So WP naught, WP naught, and then we have got T and P. So P and T, and they are being ORed, and then W and T. Remember bridging. W and T, they are being ORed again. That is how it will be solved. Pause and understand. So with this equation, WP naught plus TP, solve the whole truth table as well. Now, 4 sensors number 1 to 4 produce. Remember, 4 input means 2 to power 4. That is 16. 16 means 0 to 15. There are 16 possibilities. 16 possibilities, 0 to 15. So there are 4 sensors, and A is, let's call it sensor 1, sensor 2. So A would be 1 plus 2. This is 1, this is 2. B would be 1, sorry. B would be 2 and 3. And C will be 3 plus 4. So these numbers, digits are actually showing sensor. So sensor 1 or sensor 2 is A. Sensor 2 and sensor 3 is B. Sensor 3 or sensor 4 is C. So sensor 1 or 2. This is 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1. 1, 1, 1, 1, 1. So this is A, 2 and 3, end, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, and 1. 3 plus 4, C, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, and 1. That is how it will be solved. Remember, this is the only question we have for 16 inputs. And if you could see, let's talk it this way. If it is 4 bits binary, then this is 2 to power 0, 1, 2 to power 1, 2, 2 to power 2, 4, 2 to power 3, is 8. If it is 1, 2, 4, 8, then this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 8 and 4, 8 and 4, 12 plus 1, 13, 14, 8 and 4, 12 plus 2, 14, and 15, 8 and 4, 12 plus 2, 14 plus 1, 15. So this is just a good example for you to understand. So now X or Y, X or Y, or Y and Z, X or Y and Y and Z, or this all becomes easy if you practice. Now a student is in electronics lesson, build the following circuit, complete the truth table for this circuit. This would definitely be a tough one, but it is not always that tough. So X is equal to A and B naught, A and B naught, then plus, then let's solve this one, A and B plus A, A and B plus A and B and C, A and B and C. That is how it will be solved. So this one is A and B naught. This one is A and B here. This one is A and B again, but this is being ended with C over here. And these two are being ORed over here. And the whole result is being ORed with this over here. So there we go. Now, A and B naught. So let's solve B naught first. 1 1 0 0 1 1 0 0. Then we have A B naught. So A B naught. 0 0 0 0 1 1 0 and 0. Then we have AB 0 0 0 0 0 0 1 and 1. Then we have what? A, B and C. A, B and C. A, B and C. So this would be 0 0 0 0 0 0 0 and 1. So the result is AB plus AB and C. This one, let's call it M. So AB plus AB and C. So M would be 0 0 0 0 0 0 1 1. And what is X? X is actually M plus AB naught. M plus AB naught. 0 0 0 0 1 1 1 1. That is your answer. 0 0 0 0 1 1 1 1. That is your answer. Now it says that study the output in your answer to part A1 and state what could replace this whole logic circuit. Study the output in your answer in part A1 and state what could replace this whole logic circuit. So what do you say? So what comes to your mind? If you could observe A and X are the same. So whatever the input in A is, that is the output for X. So if you could see that A has 4 zeros, so X has 4 zeros and A has 4 ones. So what is actually happening that whatever the input at A is having an effect on X, other inputs have no effect on over the X. Now it says that write a logic expression to represent the following logic circuit. So it would be x is equal to 1 if a is equal to not 1 over here, or over here b is equal to not 1, b is equal to not 1 over here, and c is equal to 1. And for this, a is equal to not 1 or b is equal to not 1 over here. A is equal to not 1 or b is equal to not 1, and over here it is this. And now this or, so this or goes here, or this would be simply x is equal to 1. We have to put if not a or not b or not b and c. Either of them are all right. Write logic statement, logic expression, logic statement that describes the following logic circuit. Over here it would be a not multiply b. Over here it would be b not plus c. Over here it would be a not b plus b not plus c. Over here it would be c naught, and over here it would be a naught b plus b naught plus c multiplied by c naught. That is how we define x. So the logic would be x is equal to 1 if bracket 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 not a and b or not b or c and not c. That is how your answer will be. Now you can see that this particular example is with 5 inputs. So try solving it yourself. It says that the alarm sounds x is equal to 1 if the alarm is enabled. Alarm is enabled. And any one or more of the sensors is activated. So we have got sensors over here. Sensor 1, sensor 2, sensor 3. Alarm is enabled and any one or more of the sensors is activated. Any one or more means OR gate. And means and. Alarm is enabled. So we have to, an alarm X is enabled and disabled using either switch A or remote control B. So this would be A or B and C or D or E. That is how it will be solved. So C or D or E. So the equation would be x is equal to 1, sorry, x is equal to a plus b and c plus d plus e. That's your solution. So solve it. A plus b, c plus d, or e, and that's your answer. So that's about it. I tried solving as many as possible, as many questions as possible, and almost all of the parts which are required for logic gates and logic circuits for at O and AS level are covered. And whatever the exceptions that I could observe in past paper questions, I have discussed those using these past papers. And users, if there are any other questions related to this topic, as I have covered it very comprehensively, please do ask those questions under this post or in your respective groups, WhatsApp or Facebook, whatever. So thank you very much. I hope I would have made things clear to you. And if there is any confusion, any question, shoot it out. Thank you very much. Take care and bye.